Good morning, everyone. Welcome to the first video on electric fields and forces. And in today's video, we'll be discussing the solutions on concept-wide mock test, which yesterday I had shared the question paper along with it in the WhatsApp group, which is misconceptions in physics. If you want to know more about the details, you can refer to my earlier videos or you can write back to me in the same comment section, so I will be able to brief you about it. Okay, and thank you for the feedback that you people have provided me on my first podcast, which was on electric fields and forces. Though some of them suggested that I need to put more number of visuals. So usually podcasts are meant to be without visuals. That is, you talk, and it's very much useful only for those who are active listeners. Okay, and when you say you need some visuals, it means again I would like to go back to the video. And in fact, one of the comments made by one, I think, Sandeep Srinivasan. Okay, so you have very clearly mentioned that something like if there is a visual, then it will be useful for us to understand or to know about the problem more in detail. Okay, otherwise, if you just narrate a problem, you will not be able to write it down. So that I felt okay, that's a better one. So what I thought was that okay, as the podcast is going on, that is now the meaning of the podcast that I mentioned here is that my face would not be visible, nor my tone or voice will be there, but instead it will be something like it will be an AI generated tone. I actually use AI over here. So what I have done actually is that I have taken all the videos corresponding to the given concept from the YouTube. That is the videos that I have made for my past papers. Okay, and every video will span for something like 2 minutes, some of them 3 minutes, some of them a long video structured problem will be for 10 minutes and so on. I've taken all those video links, put it into one AI tool, and this AI tool turns out or extracts the information from it, the content from it, and what it does is it puts the content in a very concise way, and then it converts this content in the form of a discussion, which is a conversation between a teacher and a student. Okay, so this I found out this pattern would be quite useful. Okay, so it is not that the content is being generated by AI, it is nothing but it's not hallucinating or anything like this. One of them asked about it. Okay, if you are generating content by AI, then how will it be useful? Okay, so of course, so I am not generating the content, I am using the same content but packaging it in a different way. That's what I'm doing. Okay, and hence, so as a dialect thing that I am putting it over there, and the voices are also different. That's what is being seen. Okay. So yesterday, as I had already told you, that I'll be putting across one what you call a question paper. So this is a question paper yesterday I had shown, and in this question paper we had. I hope you would have solved these problems. So today I am solving the solutions or giving the solutions for us. Okay, let us begin with this. So 2 point charges plus 2 nanocoulomb and minus 1 nanocoulomb are present over here. A third charge of plus 1 nanocoulomb is placed along the line so that the resultant electrostatic force on it is 0. So place along the line, okay, which of the regions 1, 2 and 3 to the charge be placed. You need to put one charge somewhere so that the resultant electrostatic force is 0. Okay. If suppose if I put the charge here, if I put the charge plus q here, then what will happen? This plus q will be pushed away from in this direction. Okay. And okay, so not with the q 1 nanocoulomb. Okay, I put this is right 1 nanocoulomb plus 1 nanocoulomb. So this will be pushed like this. And what will this minus 1 nanocoulomb do? It will try to attract like this. But you know, this force would be larger than this one. So resultant force will not be 0. But what is being asked? Resultant electrostatic force should be 0. So therefore, 1 is not the correct position. Let us look at the region 2 here. If I put the plus 1 nanocoulomb here, what will happen? This 2 nanocoulomb will now try to push it like this. Minus 1 nanocoulomb will now try to attract it like this. So definitely this is also not the right position because net force is directed in this direction. If I keep the object here, if I put the 1 nanocoulomb force over here, charge over here, then what will happen? This minus 1 nanocoulomb will pull it like this. This 2 nanocoulomb will now try to push it like this. There is a possibility that the force due to the plus 2 nanocoulomb will be equal to minus 1 nanocoulomb attractive force, and hence these two can cancel each other at some point, and hence region 3 would be the right answer. Okay, next, do the second problem. The diagram shows equipotential lines in the vicinity of two equal charges. Okay, there is a positive charge, there is a negative charge. There are some equipotential lines being drawn. Which one of the arrows represent best the direction of the force that would act on a small positive charge that is placed at the point P? So what is the direction of the force according to these directions? Now here if you see, This is on this equipotential line. Now what is this equipotential line signify? The potential is same at every point over here, and then the force field is now directed in this direction. Why? Because negative charge. Negative charge will always have the field lines attracted towards it. If the field lines are attracted towards it, what will be the force? You know, force is equal to Q times E. If vector E is directed like this is your vector E, then Q being a scalar, force would also be directed like this. Now what is being asked? Which one of the arrows best represents the direction of the force that would act on a small positive test charge placed at point P? If you keep a positive charge, then the direction of the force would be radially directed inwards towards the negative charge over here. Okay, so which answer corresponds to it? The answer B over here. Okay, now let us move on to the next. Consider moving the small positive test charge from point P in the situation shown in the diagram. Okay, so there is a point P here along three different paths x, y, z. Which of the following statements below is being correct? Okay, so the work done is least for path x, work done is greatest for path x, path z, work done is 0 for path y, and then work done is same for all paths. Okay, now what is that is being shown over here? So consider path. Okay, so you have three parts over here. Okay, and on these three parts, okay, which one is seen to be correct? Now work done is seen to be correct. Now you know the electrostatic field is nothing but a central force field, which means what? It does not depend upon the direction first, and secondly, see, the force is proportional to 1 by r square. Okay, it does not depend upon cos theta, sin theta, nothing it depends. So therefore, and secondly, you observe when force is dependent on 1 by r square, you can move it in any direction. We call such forces as path dependent forces. Path independent forces. Path independent forces. What do you mean by path independent forces? Either you move like this, or you move like this, or you move like this. The work done is seen to be the same, or sometimes also called as conservative force. Conservative force, because it only depends upon the distance that you have traveled or displacement that you have traveled. So as a result of it, it is not least for any of the paths or maximum for any of the paths. It should be the same for all the three paths. So the right answer here would be work done is the same for all the three paths. D is the right answer. Okay, then which diagram could represent the electric field lines between two oppositely charged conducting surfaces? Two oppositely charged. That means two conductors are there which are oppositely charged surfaces over here. So now, if I consider this to be positive and this to be negative, positive will always throw all the field lines outwards, and negative will always attract all the field lines. See, this is correct. To see into it, this is correct over here. I'll put this correct over here. But let us explore the rest of them also. See, electric field lines will always go in a straight line. It cannot take a curved path. So definitely, this is taking a curved path. So this is incorrect. You see here, this is also taking a curved path, and moreover, it is inward. So if this is inward, might be I can consider this as positive or negative. But if this was a straight line, my assumption would have been correct. But unfortunately, it is not seen over here. Okay, so it is taking a curved path. Because of this curved path reason, I will still call this as incorrect. And D also you see as a curved path over here. Okay, electric field lines are always directed from positive to negative. First thing. And secondly, it should be only a straight line. It cannot take a curved path. Okay, now let us move on. An electron enters a region of space where there is an uniform electric field. There is a uniform electric field. There is an electron which comes inside. Initially, the electron is moving parallel to the direction of the electric field. So it is moving parallelly like this. What is the subsequent path and change of the speed of the electron? What happens to the path? Now, you know, when you have an electric field like this, how do I visualize this? I can say this region is seen to be positively charged and this region is seen to be negatively charged. Only then you can get a uniform electric field like this. And now an electron moves inside it. When it moves inside it, the positive charge, what happens? This will now try to grab this electron, attract this electron. When it tries to attract the electron, what will happen to the speed of the charge? Speed of the charge, let us say initially here, let us say something like 100 km per second. Okay, very fast moving electron, moving like this over here. Now as it starts moving, now this is trying to pull it like this over here, and this electrostatic field due to negative charges is now trying to push it like this. So what is favorable for it? The electron speed is now going to decrease over here. Okay, as it starts moving towards the negatively charged, it is going to decrease over here, and after that it's going to take a U-turn and going to go like this over here. Right? Now, which of them is right here? Path of the electron, linear, parabolic. Does it take a parabolic? Does it go like this? No, it doesn't go like that, right? So parabolic is incorrect. Definitely path of the electron is linear. Okay, so two of them are right. Now let us see what happens over here. speed of the electron. What happens to the speed of electron? See here, the speed is 100 km per second. Now as it keeps on going here, it keeps on reducing and reducing until at some point over here the electron speed becomes completely zero, which means what? The electron speed is reducing. So therefore this is also wrong. So decreases the right answer. Okay, thus A is the right option. Okay, now let us move on to the next one. Okay, welcome once again. So in the previous video we had seen about MCQs corresponding to the concept test, which was on electric fields and forces. Now what we will do is we will start doing the problems on the structured questions. Okay, so two questions were asked and these are the solutions for these two. Okay, now a light metal coated fifth ball of mass m is suspended between two vertical plates as shown. The potential difference V is applied between the plates which are a distance d apart. When the ball is charged, the string hangs at an angle to the vertical as shown. Okay, so it has been hanging like this. Now what is the question over here? So sketch the electric field lines due to the plate alone. Okay, what is the electric field lines over here? See, there's a positive here, there's a negative here. So definitely electric field lines should be like this. Electric field line should be like this over here. This is how the electric field line should be. So it should be extended until here. So this should be your electric field lines. Okay. Then what is the sign of the charge of the ball? What is the sign of the charge of the ball? See here. Now it is said that the ball is already charged. So it said that the fifth ball is already charged, but he has not told you what is the sign of the charge. So if this was positive, then this positive charge will get repelled by this positive charge and hence it will start moving like this. So definitely this should be positive charge. It should be positive charge. Okay, and hence it has been moving like this. And if this side is positive, once again you see this is negatively charged, it will attract over here. So definitely this is the right answer. Okay, we have seen this one here. We can say this is positively charged. Positively charged. Okay, next. Draw a free body diagram on figure 2 for the fifth ball hanging at an angle. Label each force. Here you need to draw the free body diagram. Now free body diagram for this. See what are the forces acting here? mg is acting downwards because you are conducting this on the earth. And then there is a tension force because there's a string over here. The tension force which is acting over here, right? And then what else do we have? We also have, there's an electric force acting here. There's an electric force acting here. I can put like this over here. Okay, so all the three I can put it over here, right? And then so see to it that the length of this tension force is bit longer as compared to this. Sorry, not bit longer, not longer. Okay, it should be here like this. So sum of these two resultant would be somewhere over here. Okay, and this length should be equal to this length. That's what you need to look at. Okay, then so by considering the work done in moving a charge between the plates, show that the electric field E between the plates is given by E equal to V by D. Now the problem changes to I have a positive charge here and this is moved from one end to the other end. In that case, show that how the electric field is equal to V by D. Okay, so we need to do it like this over here. By considering the work done, there's already given a clue here. Work done, using work done formula, arrive at it. What is work done formula? We know that force multiplied by displacement, right? Now what is the electrical force? What force is acting on the charge? There's an electrical force. What is the electrical force given by? Electrical force is given by Q into E into D. Okay, here what is Q? Q is nothing but electronic charge minus E. Anyway, I am not going to write it. I'm just going to write like this over here. Okay, now if it is not an electron, and here it says show the electric field when moving a charge. So I'll take the charge to be Q only. Okay, Q into E into D. Now we know that potential is given by the formula work done per unit charge. So what I will do is I'll substitute it over here. I'll write work done per unit charge is equal to potential. I'll divide this by Q on both the sides. So what do I get? I get E into D, W by T equal to E into D. Or in other words, I'll replace this W by Q by V. So I get V is equal to E into D. What is that I need to show? E equal to V by D. Now you can show E is equal to V by D from this expression. From this expression, I can directly transpose it and write it like this. So we have arrived at the required equation. Okay, next. The mass of the ball is 40 milligrams. What is 40 milligrams? Mass of the ball is 40 milli. Milli means what? 10 power minus 3 grams. 10 power minus 3. Always convert everything into kgs. And the applied potential difference is 480 volt. Applied potential difference 480 volt. The plate separation is 6 centimeter. Plate separation 6 into 10 to the power of minus 2 meters. If the string hangs at an angle of 20 degree to the vertical, theta equal to 20 degrees, determine the charge on the pithball. Okay, let us draw the diagram to understand what is being given. This is how it is given. Now this is a vertical, this is the angle theta, this is the pithball, this is your mg, this is your tension, and then what does it say? This is v. These are the two plates that is being given here, and here you say this distance, the distance between these two is also given to be around 6 centimeter, and the potential difference V is equal to 480 volt. Now what is being required? You need to determine the charge on the pithball. Charge on the pithball. Let the charge be Q over here. Okay, how do we do this now? Now since V and D are known, what we can do? Using V and D, you can find out the value of E. Right? So let us find out the value of E. And before that, so see, we should have a plan here. The plan here is that how do you determine this? See, this tension T, this angle theta is known. So this should also be angle theta with respect to this vertical. Now, if this is tension T, okay, I'll rub this. Then the component of T along this direction would be T cos theta, right? And the component of T along this direction should be T sin theta, right? And the electric force, because this is positively charged, and in the previous question I already told you that this will be also be positively charged, so this is repelling this one, so it's a net force Fe acting like this over here. Okay, now since it's an equilibrium, I can apply the law of forces, equilibrium of forces, and I can now say that T cos theta is equal to mg, and then I have T sin theta is equal to, see, this T sin theta is equal to Fe. Fe. I can now write like this over here. What is Fe? Electric force, right? Now what I will do is I'll divide one by the other. I'll divide one by the other. Divide one by the other. So that T cancels over here and I get tan theta here. So the tan theta is equal to Fe divided by mg. So I got this also. What's the next step? Next step is that tan theta can be inferred. Mg is known to us. M is known. G is 9.8. You can substitute that. And the Fe. So I can calculate Fe from here. Fe is equal to mg tan theta. Let me write this equation number 1. And now what is Fe? Electric force. From electric force, how do you determine the electric charge? So what you do is, we know that there is a constant electric field between the two plates. So what should I do? We know that Fe, if there is a constant electric field, okay, and there is a charge Q inside it, this will experience a force given by Fe equal to Q into E. What is to be known? I need the value of Q here. Okay. Now, so therefore, I can now write Q is equal to Fe divided by E. Let me substitute it over here. Fe is already known. So I will now take Q as a subject and I will write. So which means this should now be equal to mg tan theta divided by E is what? I just write E itself. Okay, I need to get the value of E. See, all this known, only this value is unknown to me. How do I determine the value of E? Let me see here. See, I already told you beginning, V and D are given. You can find out the value of E. How do you find the value of E? You can find it out by writing E is equal to V by D, right? So what I will do is, I'll find out this value. I will write E is equal to, what is the value of V? Value of V is 480, D is 6 into 10 power minus 2. So this should be 480 divided by 6 into 10 to the power of minus 2. When I do this, I get 6 ones are 6 80s are. So I get 80 into 10 square. 10 power minus 2 goes up for 10 square volt per meter, which is equal to how much? Which is 80,000 volt per meter, 8000 volt per meter. Now I have everything. I can substitute this here. Now let us substitute all this. What's the value of M? M value is 40 into 10 power minus 3, 10 power minus 3, which is 40 into 10 power minus 6. 40 into 10 power minus 6 multiplied by G, 9.8 into tan 20 divided by what's E? 8000. 8 into 10 cube. I'll write like this only. So 4, 8 ones are 8 fives are, right? And then 5 8s are 40, 4 5 9s are 45, 49. I guess the answer is 49, 49.0 multiplied by, there's a 10 power minus 6, there's a 10 cube over here. When it goes upwards, it becomes 10 power minus 9 over here. And I need the value of tan 20. Let us use the calculator to get that value also. So I have now, let us take 20, 20 and then take tan 20, tan 20 I got, multiply this by, I use tan 20 is equal to so much, multiply this by 49. 49, I get the answer here as 17.83. I get the answer as 17.83 into 10 to the power of minus 9. What is this now? This is nothing but your charge over here. Coulomb. Okay. Or in other words, you can say this is 18 nanocoulombs. Okay. This is how you can answer this. Okay. Now, such a big calculation. How much marks is it? 6 marks. Wow. Great. No? So, if you do so much, really worthwhile. Right. Then, an arrangement like this can be used to serve as a charge measuring device. How would you make the device more sensitive to measure smaller charges than the above? Okay, so it's a wonderful arrangement to find out what is the amount of charge which is being present in the fifth ball over here. What is the amount of charge present here? You just take two plates connected to positive and negative terminal, high applied voltage, and then by monitoring the angle, you can easily find out what is the charge percentage. Now, what he says is, this charge that we have found out is nanocoulomb, 18 nanocoulomb. But I don't want 18 nanocoulomb. I want to find out with a much lesser value also. So what method, what is the changes that you would like to apply? Now, to understand this question, what you do is you substitute all the values once again. Get the formula first. E is equal to mg tan theta divided by E. And we already know E is equal to V by D, which can be written as mg tan theta divided by E is what? V divided by D, which should now be equal to mgd tan theta divided by voltage. Now, what is he asking? I want to get lesser values of Q. Lesser values of Q. If I say lesser values of Q, what should I decrease here? Can M be decreased? M cannot be decreased. M is already very, very small, 40 milligrams. 1 gram would be something like a tiny speck. Okay, 40 milligrams will be much, much lesser. Okay, don't look at the number 40. It is about the milli over there. Okay, it's 1 gram and 40 milligrams. So definitely it is much, much smaller. So I cannot reduce this value. I am going to conduct this experiment on Earth, so therefore G cannot be changed. Okay, D. What is D? See, if you take two plates, it says in this arrangement the two plates are being kept at a distance of 6 centimeter. 6 centimeter is this much big. Do we need this much big? I don't think so. So why don't we reduce this? Can I reduce it to 1 centimeter? Okay, possibly there. You can always reduce the value of D. Okay, so therefore D can be reduced. If D can be reduced, definitely even if D is hard, instead of 6 centimeter, if I put it as 3 centimeter, I can now determine the value of Q to a much lesser, maybe around 9 nanocoulomb also. Okay, good result in that case. Then tan theta I can't reduce because it depends upon the electric field, right? I cannot make theta to be 20 instead of it. I can't make it 10. It depends upon the equilibrium condition. What about V here? V, I have used 480 volts, but there are devices where you can use thousands of volts also. So you can increase the voltage between the plates. Okay, when you do this, definitely if V increases, 1 by V decreases, or the value of Q also decreases. So therefore, either I decrease the value of D or I increase the value of V. So what I can do is, for example, I can say D can be made as D by 2 and V can be doubled. Okay, when I do this, what will happen? Then the charge can be made 1/4 of it, right? You can still find out the least charge, which is 1/4 of it, which is 18 divided by 4. How much will this be? 4.5 nanocoulombs. You can go until 4.5 nanocoulombs. The least charge that you can determine here would be 4.5 nanocoulombs. You can do it like this also. Okay, so thus you can do all these things. Now let us move on to the next question. A charged particle is situated in a field of force. Right. A charged particle is situated in a field of force. Deduce the nature of the force field, magnetic, electric, or gravitational when the force is on the particle. This particular question, it revolves around several concepts. Okay, though I have stated that we are looking only at the electric forces and electric fields, but of course it uses electric forces, electric fields, magnetism, mechanics, everything it brings into. In fact, IB papers mostly rely on multiple chapters. You don't get only a straightforward question. So that's what I thought this question would be very useful so to understand. Though I have not covered everything, Okay, so in my lecture notes, but still what has happened is that, so if you do these kinds of questions, you will get to know like how cross-disciplinary questions can be asked and how it can be answered. Okay, so really a very long or a lengthy question. Then deduce the nature of the force field when the force on the particle is along the direction of the field regardless of its charge and velocity, which means what? See, I have taken a charged particle q. Okay, now if I take another charged particle, it is 5q. Now first, okay, if I take a charged particle q and I find out the field, then the field be E over here. Okay, now if I take a charged particle 5q, even then if this is the same field, okay, so when can this happen, or what kind of field are we talking about? See, when you change the charge, electric field will definitely change. Okay, so nothing over here, no changes over here. Now if you have an electric charge and it is moving, okay, velocity, okay, then what will happen? Magnetic field will come into play. Now what does it say? Whether you take an entity, you take a particle, okay, the particle should, if you change the charge also, the field should not change. That is not possible in electric field. If you change the velocity of the particle also, the field should not change. That means it cannot be a magnetic field. Then which particle can it be? It only, what kind of field should it be? It should only be a gravitational field. It will only be a gravitational field. In a gravitational field, it only depends upon the mass. Is there anything mentioned about the mass over here? No. It only says, okay, regardless if there is along the direction of the field, regardless of the charge and the velocity. So therefore, it does not depend upon these two. So therefore, it is a gravitational field. Then it's independent of the velocity of the particle, but depends on its charge. Which one depends only on its charge, not on velocity? K q divided by r square, which is this electrostatic field. Electrostatic or electric field depends on the velocity of the particle and its charge. It depends on both. Very clearly, they should be magnetic. Okay. So this question is about understanding the differences between three different fields. Okay. Attempt this and definitely you will be able to understand the entire full chapter of how electric field and magnetic field are connected. Then an electron is accelerated from rest, which means what? Initial velocity is equal to 0 in vacuum through a potential difference of V is given to you. Deduce the final speed of the electron. Now, when you have a particle of charge q which is moving, okay, which has been accelerated with a potential difference of V, then the work done by the field in order to make it move is nothing but q into V over here. When you do say I am doing some work on the particle, what happens to the work? Which means the particle is now moving and it is stored as its kinetic energy. Now, so therefore, I can now say this work is now stored as a kinetic energy. I can now write this as half a v square, right? Don't cancel this capital V and small v here. These are different. V is potential difference, small v is the velocity of the particle. These two are two different things. So you need to determine, you need to prove V is equal to so much. So how do I prove? I will now do something like V square is equal to 2qV divided by M. Or in other words, if I remove this V square, then I will get this as 2qV divided by M square root. Now let us substitute all the values over here. V is equal to square root of 2 into, what's the charge? Charge, what is this now? Electrons accelerated, electron. 1.6 into 10 to the power of minus 19 multiplied by V 2.1 kilovolt, 2.1 into 10 cube divided by mass 9.1 into 10 to the power of minus 31. Let us do this and see whether we are getting the correct result or not. We'll just make calculators here. Okay, so this should be 2 into 1.6 into 2.1 divided by 9.1. When I get this, I get the 0.7384. 0.7384 multiplied by 10 power minus 19 plus 3, minus 16, minus 16 plus 31. Let me do this. So I have minus 16 minus 31. I get this minus 15, right? So this goes upwards. So this should be positive 10 to the power of plus 15. Okay, and this is square root. We'll put the square root over here. Okay, now doing this in a calculator will be very much difficult. So what I will do is I will just take this, or I'll write this as 7.384 into 10 to the power of 14. I'll write like this. Okay, because 10 power 15 means I have to add 15 zeros, which is very difficult for me to do it in my calculator. So I write like this over here. Now I can solve this. Okay, take the root of 7.384. 7.384 square root of this will be 2.717. Will be 2.717 into 10 to the power of 10 to the power of 14 whole to the square root should be 10 power 7. So in other words, this should be 2.7 into 10 to the power of 7 meter per second, and that is what I need to prove. I've done this. Okay, now let us move on to the next one. The electron in B then enters an uniform electric field between two horizontal metal plates. Okay, the two horizontal metal plates. 95 volt is given here. 95 volt, 0 volt, which means what? This is heavily positively charged. This is positively. This is negatively charged. Okay. Next question you can always guess. The moment it enters here, what will happen? This will go and attract, go and stick to this one. Okay, because it will never come downwards here. Right. The electric field outside the region of the plates may be assumed to be 0. The PD between the plates is 95 centimeter and distance of separation 2 centimeter. See, if the value of V is given and D is given, then you can find out the value of E. Okay. So always remember, if at all he gives you something, that means he is asking you something to do. Okay. So you can easily determine this. Then as the electron enters the region of the electric field, it is traveling parallel to the plates. Oh my God. See. Now the electron enters it, it is traveling parallel to the fields. Okay, it is not going towards it. Let us see why. Do not know. Let us see. Take that also. On the diagram above, draw an arrow at P to show that the direction of force due to the electric field acting on this on the electron. Draw an arrow at P. Draw an arrow at P. What is the electric force acting? I have already drawn. This is the electric force acting. Fe is acting like this. Maybe it takes some long time. It will go all the way along until here. It might take something like this, and finally touch at some point. Okay, or maybe it may go, it may escape like this also. It may escape like this. Okay, and finally it may go out also. I do not know. Let us read the full problem, then we will understand. Okay, then so we have drawn this one. Then next is calculate the force on the electron due to electric field. Force on an electron. What is force on an electron? If there is a charge particle and if it is moving in an electric field, what will happen? This charge particle will experience a force which is given by 2 times E. Okay, what is Q? 1.6 into 10 to the power of minus 19. And what is E? Is the value of E given? No, but you can always determine. How? See, E, I told you, if V is given and D is given, you can find out E. How do you find E using V and D? Very simple formula. So E is equal to V divided by D. Now what is V? Which is V? Let us find out what is V. 95 volt. And what is V? 2.2 centimeter. Okay, let us substitute that. So 95 volt divided by 2.2 centimeter. Right? So let us calculate this using my calculator. 95 divided by 2.2 will be around 43.1818. So this should be 43.18. I'll write it down here first. 43.18 volt per centimeter. But the centimeter, when it goes upwards, this will become 43.18 into 10 square volt per meter. Right? So as a result of it, this will be 4318. I'll do one thing. I'll write like this here. 4318. Okay. Next, what do I have? I need to multiply these two. When I multiply this, 4318 multiplied by 1.6 will give me 6908. 6908 into 10 to the power of minus 19. Correct? Let us check it out once again. Are we doing it correctly? 4. Yeah. So I have 2.2 centimeter, 95 volt. Everything is right. So this is what? Newton. Or in other words, I can now write this as 6.9 into 10 to the power of 123. 6.9 into 10 to the power of minus 16 Newton. This is the force that acts on the electron. Okay. The plates in the diagram opposite are of length 12 centimeter. Okay. So this length is 12 centimeter. Right. Then determine the time of flight between the plates. So what's happening over here? Projectile motion, nothing else. Okay. But the projectile motion is a difference. So you have the two plates. This length is 12 centimeter. Electron is here. The electron is now moving like this. Now what's happening? There is a positive charge here. So now this will describe a projectile motion like this. Maybe I don't know whether it will touch here or it will just keep on going like this. And how is it a projectile motion? If you ask me this question, in projectile motion, what did you learn? You had a cliff, horizontal projectile motion. You throw the particle from here. The particle kept on going like this and fell over here, right? What was pulling it? Gravity was pulling it like this over here. Gravity was pulling it like this. Here, what is pulling it? Electric field is pulling it like this over here. Electric field is pulling it like this over here, right? So therefore, both are same. Here is upward projectile, there it is downward projectile. Simple, nothing else. Okay. Now what we do is the time of flight we need. Now here, if I want time of flight, what do we do? We put t is equal to square root of 2h by g. Okay. Now what do you put? That's the question over here. So towards it, what you do is this distance is known, 12 centimeter. R is equal to distance length is known is equal to initial velocity u multiplied by time over here. Okay. Now if you go back over here, how is the electric field? The electric field is like this. Will this electric field affect the horizontal velocity? It will not affect. If it was in this direction, suppose if I had kept the electric field like this, and in that case what can happen is it would have pulled the electrons motion. Now it's not happening. This electric field is now going to deviate it like this. It's not asking you the net speed. Okay, it's asking you only to, in order to calculate this. Okay, we just need only the horizontal velocity. Remember, we are solving problems on a using Euclidean geometry, three-dimensional geometry. Then in that case, when you use an Euclidean geometry, we assume something here. In a three-dimensional motion or in a two-dimensional motion, what did we do? We assume the basic premise saying that one dimension is independent of the other one. Okay. If you are computing this motion, then look only for this motion's parameters. Don't worry about that one. Okay. The only thing that can combine these two is the time. That's what we did in projectile motion also. The same logic we are going to employ here. And now what we do is we use r equal to ux into t. What is r? 12 centimeter. 12 into 10 power minus 2. Should be, what is ux? We already found out. What is the ux value? Ux value is 2.7 into 10 power 7, which is already given to you. 2.7 into 10 power 7 multiplied by time theta. I do not know what is the time theta. I need to find out this. So therefore, t should be equal to 12 divided by 2.7, 10 power minus 2, 10 power plus 7. Let us do this value. Let us do this value. So this, what we get here is 12 divided by 2.7 will give me 4.44. 4.44 into 10 power here minus 2. This plus 7 goes 10 power minus 7. This becomes minus 9 seconds. Thus, the time of flight between the plates is seen to be 4.44 into 10 power minus 9. Two significant figures. I will write 4.4 nanoseconds. 10 power minus is nanoseconds, right? Okay. Then the vertical distance moved by the electron during the passage between the plates. Okay. Now what's happening? So this is your plate. This is your plate. An electron is moving like this, very high velocity. But the time it takes to cross this one is 4.4 nanoseconds. Very, very tiny time. Okay, it's not taking 5 seconds, 10 seconds. If it had taken such a long time, definitely it will come and hit here. Now, since it is taking a very short interval, definitely it go like this over here, right? It will never touch the plate. But what is he asking is that what is the vertical distance moved by the electron? So therefore, let me assume this is the baseline. This is the vertical distance it is moved. Now, how do I find it? Okay. Now, why should it move? Because there is a y acceleration there. Y acceleration. So how do I find y acceleration? Now let me call this distance y. So we know that the vertical distance moved is equal to ut plus half at square, right? What is u? U is 0. 0 plus half into, what is a? A is the acceleration along the y-axis into t square. T you already know. If you know the value of ay, you can easily do it. Now how do I get the value of uy? That's the next question. Okay. So we know that there is a force acting here. What is the force acting here? Q times E. Which E? Electric field over here. Q times E. Now this should be, according to Newton's law, M times E. What is A? Acceleration. Which acceleration? Acceleration along the y-axis. The force is acting only along the y-axis, nothing along the x-axis. That's why I said the horizontal velocity remains constant. It is very similar to that of what you learned in projectile motion. M into A. So now what I do is I can easily find out from here. I can find out AY is equal to QE divided by M. Okay. Now Q is 1.6 into 10 to the power of minus 19, and the value of E. Have I found out the value of E? We have already found out the, we already got Q into E here. 6.9 to the minus 16. Okay, we'll substitute it here. No need to do all these things. 6.9 into 10 to the power of minus 16 divided by mass of an electron, 1.6 into 10 to the power of minus 9. Sorry, not mass. This one mass is 9.1 into 10 to the power of minus 31. Okay. Now let us calculate this value. AY is equal to, let us take 6.9 divided by 1.6, sorry, 9.1, which will give me 0.758. 0.758 into 10 to the power of, here minus 16, here plus minus 31. When it goes upwards, 31 minus 16. How much will this be? 31 minus 16 will be 15. So 10 to the power of 15 meter per second square. Very, very huge acceleration. Okay. So AY is equal to so much. And this I can now write this as 7.6. I can approximate, and I can write this as 10 to the power of 14 meter per second square. Okay. Now let me substitute it over here. When I do this, I get this as 0 plus half will be half into 7.6 into 10 to the power of 14 multiplied by t square. What's the value of t? Where is t here? We found out 4.4 nanoseconds into 4.4 into 10 to the power of minus 9 whole square. Now let us do the math here. Lots of calculation, but generally reveals a lot of information. 4.4 into 4.4 into 7.6 divided by 2. I get 73.568. Let me take 74. 74 into 10 to the power of, here it is 14 and here it is minus 18. Minus 18, which will be 74 into 10 to the power of minus 4 meter. Will be equal to how much? Will be equal to 0.74 centimeter, right? Is this centimeter? Yes. 0.74 meter or 0.74 centimeter. Now, if you look at this, whether this is correct or not, okay? If you look at this here, what is the distance here? 2.2 centimeter. So, what does it move? It has moved by a distance equal to 0.74 centimeter. Okay, that means it has already escaped from the plate. It is not in the vicinity of the plate. It doesn't come to the plate, and it has already escaped. Okay. Now let us move on to the next question. You have done all this. Suggest why gravitational effects are not considered when calculating the deflection of the electron. Why did not we consider gravitational effect? Very simple. So gravitational field is, sorry, not gravitational field. Gravitational force is much lesser than the electric force, right? So what is the value of gravitational force? If you want, you can compute and show also here, which should be equal to m into g, which is what is the mass of the particle? Mass of the particle, where is it? Mass of the electron. So it was a particle is nothing but electron, which comes out to be, if I just take the magnitudes of it, 9.1 into 10 to the power of minus 31 multiplied by g, I take this 10 over here. Even then, I get this as 10 power minus 30 Newton. And if I take electric field, what is that force that I have taken? The force due to electric field is 10 power minus 16. It is merely 10 power minus 16 Newton. So which means, you see, you compare between these two. So you see that Fe or Fe by Fg, if I do Fe by Fg, if I do, I get 10 power minus 16 by 10 power minus 30, which happens to be 10 to the power of plus 14, which means what? Fe is 10 to the power of 14 times Fg. It's not one time or two times. It is 10 to the power of 14 times. As a result of it, there is no point in considering the gravitational effects, and hence gravitational effects have been ignored. Okay, so this is what we have to say. Then next, just a minute. Okay. In a mass spectrometer, electric and magnetic fields are used to select charged particles of one particular speed. You know what is a mass spec, right? Mass spec is something like, you have certain charged particles. When the particles comes across, You can actually separate the particles based on the mass of the particles and the electronic charge. A uniform magnetic field is applied in the region between the plates such that the electron passes through the plates without being deviated. For this field, state and explain its direction. Now, what does it say? So you have the plates once again, and you have an electron which is moving like this over here. Now definitely electric force is now making it to go like this over here. Now what you do is you put a magnetic field here somewhere inside the plates so that there is no deviation, which means what? So there should be a downward force acting downwards so that the electron just goes straight like this. If this has to happen, what should be the case? This Fe should be equal to Fb. Okay, Fe should be equal to Fb. Just a moment, let me pull this down. Fe should be equal to Fb, first condition. Now if Fp has to be pointing downwards, then what is the direction of the magnetic field? That's what you need to ask. How do you determine direction of the magnetic field? You will determine it using Fleming's left hand thumb rule. Okay, how do you use this? Now you say, for example, usually this is the easiest way to determine, right? If the magnetic field is pointing inwards, okay, I'm not saying conclusively, if it is pointing inwards, they will modify this if you need. Okay, pointing inwards, and I is the correct. Okay, B is like this, I is like this over here. Then what can happen is forces in the upper direction, which means if this was a positively charged particle, then the particles would have got absorbed upwards or will have an attractive force upwards. Since it's a negative force, then what can happen? I can flip this thumb downwards, right? I can flip this thumb downwards. When it downwards, that means what? There's a force acting downwards. That is the reality, right? I want the magnetic force to be applied downwards. So this is possible only for an electron moving like this, and the magnetic field should be indicated downwards. So now we can say the magnetic field should be directed downwards. Okay, so state and explain its direction. So what you should do? You should say, okay, Fe is equal to Fe. This will carry 1 mark. Then use your FLHT. You explain why is it happening, and then you put across the magnetic field. Deduce the magnetic field is pointing downwards. Okay, next. Determine its magnitude. We need to determine the magnitude. So what's happening once again? Fe is equal to Fb. Fe already you know. What is the value of Fb? Fe value is given here. What is the value? This is 10 power minus 16. Let me take the exact value of Fe. Fe value 6.9 into 10 power minus 16 Newton. Let us take that value. So I will take 6.9 into 10 to the power of minus 16 should be Fb. What is Fb? Fb is a QVB, right? This Q is electron. V already the velocity of the electron. We know that. B you can find out. So B should be equal to 6.9 into 10 to the power of minus 16 divided by Q 1.6 into 10 to the power of minus 19 multiplied by V. What is V? 2.7 into 10 to the power of plus 7. Okay. Now take all these values, substitute, and we will get the answer for that. So I will get this as 6.9 divided by 1.6 is equal to 4.3. This divided by 2.7, I get the answer is 1.59, which is 1.6. 1.6 into 10 to the power of, here it is minus 19 plus 7 will be minus 12. Minus 12 and goes upwards, it will be 10 power minus 16 plus 12, which will be 1.6 into 10 to the power of minus 4. What is the unit? Tesla, right? Minus Tesla. So this is your magnetic field over there. Okay, you can also write this as 0.16 millitesla, right? The electric and magnetic fields in Fr remains unchanged. Giving an example, brief example, explanation in each case. Compare qualitatively the direction of the force deflection of the electron in F with that of an electron traveling at a greater initial speed, which means what? The value of E, value of B are unchanged. Okay, but what's happening over here? The initial speed of the electron is increased. What was the initial speed? V was 2.7 into 10 to the power of 7 meter per second. That was the initial speed. Now what I do is I will increase the speed to something like around 3 into 10 to the power of 7 meter per second. That's what you see, right? Greater initial speed. Now what can happen? Now if this is increased, now let us write down separately the forces. Fe, the electric force, is given by Q times E. Is there a velocity here? There is no velocity here. So this will not get affected. It will not get affected. What is Fb? FB is nothing but QVB. B is same, E is same, Q is same, but V is changing. V is increasing, FB will increase. When FB will increase, what will happen? This is the plate and FE is acting like this, FB is acting like this, FB is acting like this. Now the vectors appears to be, this would be your FE and this would be your FB, longer vector. When you have longer vector, which means what? There will be a net force acting downwards, right? So because subtraction, when you do subtraction, you'll have some net force acting downwards. When you have net force acting downwards, what will happen? The electron will get deviated like this, right? So what happens? Okay, now let us move on to the next one. A proton having the same speed. Now the question changes. Okay, so wonderful question. Once again, these are all positively charged. Now instead of an electron, I replace it with a positive charge. When you have a positive charge, what will happen? This positive charge, when it comes inside it, okay, so this will get repelled by the electric field because it hates the positive charges hate this, so they will be pushed downwards. Electric force has changed its direction. Then what happens to magnetic force? Magnetic force, you see, this is your QVB, right? So therefore B is directed once again in the same direction. I is into like this, force is like this over here. Now the magnetic force is like this over here, right? Now will the FB1 FE be equal? Will it go still straight like this or will it come down? That's the question here. See, let us read the question. So compare qualitatively the deflection of the electron. He is asking you about the deflection. Now for the deflection to happen, FB should not be equal to FE, or so that something like this should change, right? So here FB in this case would be capital QV into B, right? Q is different. This Q is a charge on the proton. FE is equal to capital Q into capital B. Now what has happened is the directions of electric and magnetic fields have changed, but the magnitudes of this are equal. Of course, the values of FE and FB has also changed, but these are equal over here, right? So since they are equal, you would still expect this to go straight only. Okay, they will not change the direction. They will still go in the same direction because this V and B will give you some value, E is some value. These are not going to change over here. It's only the Q change over here. If the magnetic force is scaled up by this much, okay, by a larger value of Q, electric force is also scaled up by a larger value of Q. So as a result of it, it will never change, right? Sorry, not larger value, that is the sign. Sign is changing. Q is changing here, so it will not change. So therefore, it will go the same way because the charge on a proton, charge on an electron is same. Okay, so therefore, it will not change. Then, an alpha particle having the same speed. Alpha particle, what is alpha particle? Alpha particle is, it has 2 protons, 2 neutrons. We already said that, okay, see what is the difference between this particle and a proton? The mass for an alpha particle is 4 times the mass of a proton, and the charge of an alpha particle is equal to charge on an alpha particle, I write like this. This is wrong. Q of an alpha particle is equal to 2 times Q of a proton. Okay. Now therefore, now what will happen to the forces over here? Alpha particle is coming here. Big alpha particle is coming here like this. Now what is Fe? This is your positive charge. So therefore, Fe will act like this over here. What is Fb? Fb once again will act over here. Fe will be equal to Fb once again. So it just go deviated over here. Why it is equal to? Because Fe is given by Q times E and Fb is given by Q times V into B. So once again, this means scaled up. So in the previous one, here there was no scaling up. Here it's only the change in the sign of the particles, sign of the charge. But here it is getting scaled up over here. So as a result of it, still both of them are getting scaled up with the same value, and as a result of it, the alpha particle will still move in the same direction undeflected. Okay. So with this, we come to an end to this question paper. I hope you have solved all these problems successfully, and if you are not able to solve, okay, and you met with some difficulty, some problems, some conceptual problems, then you can always write back to me. I'd be happy to make a new video on that particular concept, whichever you have not understood. Okay, so next video would be only on electrostatic potential. We'll be discussing on electrostatic potential. You can have a look at it. So how does it work and so on. So I hope this was really helpful for you. Thank you for being with me and increasing my number of views. As of today, it has crossed more than a lakh views. So thank you very much. Do like, share, and subscribe my channel for more updates. And this will really help me out, okay, in making more problems. It is some kind of encouragement to me. And thank you once again.